Right. Yesterday, I gave you an example to do for homework. Calculate the energy of a photon of light having a wavelength of 2 times 10 to the minus 10 meters. Am I right? And your formula is E equals HF. Right. Now, I haven't given you the frequency, I've given you the wavelength. You've got two ways of doing this. One way is to say that F is equal to C over lambda. Am I right? Right. So then that would therefore be, E equals HC over lambda. You do it that way. H is 6,63 times 10 to the minus 34. C is always 3 times 10 to the power of 8 if it's light traveling through a vacuum. And the wavelength they give to you as 2 times 10 to the minus 10. And what does that work out to be? If my answer is correct, 9,95 times 10 to the minus 16 joules. Who did it that way? That's fine. No problems. Others may have said, well, F equals C over lambda. Done that calculation first. 3 times 10 to the power of 8 over 2 times 10 to the minus 10. And that's going to give you 1,5 times 10 to the 18. Am I right? Hertz. And then substitute that into that formula. Therefore, E equals Planck's constant, 6,63 times 10 to the minus 34, times this answer here, 1,5 times 10 to the 18. And that's going to give you what? Same answer. 9,95 times 10 to the minus 16 joules. I'm happy with either way. Yes. Mm-hmm. Try not to use that formula. You can, you did it correctly. Yeah. So you worked on a wavelength, how many times, how many waves in that? Oh, yeah. Okay, go to the formula. Simple. There you are. Okay. Now, the main thing is that you've got to realize that's a nice simple formula. It's easy. But we're not always going to give you the frequency. We could give you the wavelength instead. We could give you the period instead. Okay. But from the wavelength, you can get the frequency. From the period, you can get the frequency. So it's not a problem in the end. Right, let's move from there and let's have a look at another formula which you've got on your sheets in front of you. And this has to do with calculations. What we dealt with yesterday was the photoelectric effect. Do you all remember that? Can anyone tell me a little bit about the photoelectric effect? Hands up? No hands up? Why not? No, didn't have anything to do with the dual nature of light. What do you call a light particle? Photon. What determines how much energy a photon carries? Its frequency. If a photon of green light is not able to knock an electron out, will doubling up the green light help? No. What do you call it when I say I double up the light? The intensity won't make any difference. What must I change? The frequency. So give me a frequency that's higher than green light. UV. Would blue light? Well, it's higher than green. So blue may be higher. Yeah, it is higher. Whether it's high enough, we don't know. What's your range from infrared? Then we hit red, orange, yellow, green, blue, indigo, violet, ultraviolet, etc., etc., etc. So blue is up from green. It has got a higher frequency. Whether the frequency jump is enough to be able to emit an electron, we don't know. So right, let's say, well, you listen first, you can ask questions later. There you've got a piece of metal, okay? There you've got a piece of metal. Let's say it's zinc. Let's place an electron inside that zinc there. It's near the surface, but it's not on the surface. It's not lying on the top. Now, a photon of light arrives. We'll draw that in red. Here comes a photon. And that photon is moving here. And it's going to hit here, and it's going to penetrate and give its energy to that electron. Okay? Now, it can be calculated how much energy the electron requires to wiggle out of there. And that energy is called the work function. And it is abbreviated W for work 0. Okay, that's the work function. I'll repeat what the work function is. To take that electron and pull it out so that it's now being pulled out of the metal, but only just enough energy to just get it to the surface. That electron's still going to lie there on the surface. It hasn't got enough energy to take off. Okay, so you've just given it enough energy to get out of the zinc and lie there. That is what we call the work function, W0. Let's choose nice, easy numbers. Okay, let's say we've got a photon, and you're not going to get nice, easy numbers like this, that is carrying 9 joules of energy. Okay? And the work function for that electron is 10 joules. Will that photon be able to knock that electron out? No. Okay? It won't be able to knock it out. So, let's say I up the frequency from red light to, what do you want to make it? We don't have orange cokey. Blue. Okay, right. Coming there with 10 joules. Would that photon have enough energy to get that electron loose? Yes. Yes, it will get it out, but where will that electron be? Lying there, exhausted. Just enough energy to, okay, it's like someone who's caught in a riptide, and they swim and they just make it to the beach and they collapse on the beach. Okay? He's used all his energy just to get out of the water. Someone who's a little bit fitter will get out of the water and still be able to run up the beach. He'll have energy. Okay. This photon gave it just enough energy to get to the surface and no more. Okay. Right. Now we go with a different type of light. And let's hope that this cokey works. I don't think it will. But you can imagine. Yes. Beautiful black line there. And it's got, what's that number? 12. Okay. Right, let's write it. 12 joules of energy. Now, how much energy does this metal require to rip an electron loose? What is the work function for this metal? 10. Is there 10 joules there? Yes. So that electron will get there, and then it will still have how many joules left? It will still have 2 joules of kinetic energy. That's its kinetic energy that it has. It will shoot off out of the light. So it will actually take off. Yeah, so you'll actually knock electrons. The light will shine there and electrons will take off. Right. So now we've given you a formula. And that formula is the following. Let's get it the same as your book. The kinetic energy, we call it EK max. Or sorry, yeah, EK. Okay, of the ejected electron, the electron that's been knocked out, is equal to what? the energy of the, which we call, so that's the energy of the photon, do you agree? Minus the energy, what do we call the energy that's required to rip it out? The work function. You all agree? Now don't get silly, it's quite simple. Right? How much energy did this electron have once it was knocked out? 2 joules. There you are. Okay? How much energy did the photon have that was shone on? 12. How much energy was required to work it loose? 10. How much did that leave over? 2 joules. So in this case, the energy of the incoming photon was 12 joules. What was the... No, sorry. Okay, the energy of the incoming photon was 12 joules. What was the energy required to work it loose? 10 joules. And how much remaining kinetic energy did it have? You subtract that, you're going to have 2 joules. It's simple, it's easy. I mean, it's baby stuff, this. Not difficult. Okay, so you don't have to get all panicky about it. It really is simple, straightforward stuff. Let's take that formula a little bit further. What is the formula for EK? Half mv squared, and that is V max. That's the maximum velocity it can have, because there may be other losses of energy. So the maximum velocity that that electron could have would be that, or the maximum kinetic energy it could have would be 2. It wouldn't be able to have 3 joules of energy, would it? Because there were only 12 joules being bombarded, 10 joules to work it loose, that could leave a maximum of 2 joules for kinetic energy. Maybe even a little bit less if there were other energy losses. Okay? So half mv squared is the same as EK max. What's the formula for the energy of a photon? HF minus the work function of that metal. There's your formula. That's the way I like the formula. The energy of the electron, the kinetic energy of the electron, is equal to the energy of the photon minus the work function. Right. You've got it there in your notes. Let's have a look at it. Another formula, HF equals W0 plus a half mv squared. That's just taking this the other way around. HF to that side, W0, etc., etc. Okay, or take W0 across. I prefer the second version of it. I'm not too sure what's in your data sheet. You can have a look. You may want to have a look at what is the definition of the work function. Let's just have a look. It's written in there. The work function of the metal is the energy needed to only just remove an electron from the surface of the metal without it having it's any kinetic energy. Without it having any kinetic energy. So I'll repeat it. The work function is the energy needed to just remove an electron from the surface of the metal without it having any kinetic energy. Happy with that? Right, I'd like you to do that first example, please. Right, we've got 20 minutes to finish quite a bit of work, so get moving on it. That first example, I'll read it. Calculate the kinetic energy of an electron emitted from the surface of a metal having a work function of 1.2 times 10 to the minus 15 joules. So that's the energy required to work it loose when light with a frequency of 2 times 10 to the 18 hertz is shone onto it. Okay, do that quickly. Right, for those who are not sure what we're doing, we all got this answer. Who didn't get this answer? Okay, there's your formula, there's your substitution, there's your answer. If we said this is the kinetic energy of that electron, use another formula that you know from dynamics and from mechanics, use another formula to calculate the velocity of this electron. Maybe it's not. Okay, or is it greater than the speed of light? No. It will be incredibly high. Right, let's have a look. EK equals a half mv squared. You all agree? We're asked to find V. We know that the EK is 1,26 times 10 to the minus 16. Half is a half. What's the mass of an electron? You looked it up in your data sheet. 9,11 times 10 to the minus 31 kilograms. V squared. And from this, you can get that V equals, what did your answer come out to be, Matthew? 7,59. 759. Yeah. Give it to me in scientific notation. 7,60, yes. Is that the wrong answer? Okay, your answer, Taylor? You tell me it's the wrong answer, we can't give me the right answer. 1,66 times 10 to the 12. Faster than light, not possible. You didn't square it. 10 to the 12 meters per second. That's probably not possible. Okay, but nonetheless, you know the method of doing it. To the 7. So still the 1,66 times 10 to the 7. It is possible. Yeah, it is fast. Right. Only second position in the race though. Hasn't beaten light yet. Right, people, I'd like to give you another example. Same as this. Exactly the same. Okay, so let's take it down. No, not number 2. Not number 2. You can take this example down. You can call it number 1.5 if you want to. Why not? Why must sums be whole numbers? Okay, number 1.5. Calculate the EK of an electron emitted from the surface of a metal. So from the same metal surface as in question 1, quickly, because I've still got to show you another few things. So we're going to go into your break time. What's the difference between this number 1.5 and number 1? I haven't given you the frequency, have I? What have I given you? Wavelength. Can you work out the frequency from that?
Sorry, just to say this is an interesting thing.
Am I right in saying that with this section of work, you're never sure, am I working with frequency, am I working with wavelength, am I working with what? Because you've all got these numbers that are 10 to the minus massive numbers, am I right? It takes practice, and the back of your chapter on this work has got plenty of examples on it. Use them. Go through those examples. They're good examples. So it doesn't have enough energy. Interesting. So you're not going to have enough energy. No, that's true. That's true. Okay, that's good. So you can do the calculations. What's your formula? EK max is equal to HF minus W0. You all agree? But do I have F? So how am I going to change that formula? H C over lambda. C over lambda is F. You all agree? Who doesn't agree? Okay, and let's see what the energy of the photon is. I don't think the energy of that photon is enough to overcome the work function. Right, let's have a look. 6,63 times 10 to the minus 34, that's H. C is 3 times 10 to the power of 8. All over, frequency, the wavelength is 2 times 10 to the minus 10 minus the work function, which is the same as that, 1,2 times 10 to the minus 15. What does that lot work out to be? What is the energy? Could someone just do this calculation here and give me an answer for just that part? Nine, comma, times 10 to the minus 36. Not much energy that that photon is carrying. Minus the energy of the photon. Okay. So therefore, you're going to get a negative answer. So the energy of the photon is not enough energy to overcome the work function. Right, so that would be your answer. You're going to get a negative answer. Doesn't matter what it is. Your calculator can't handle it. Okay. But the main thing you would need to say, the answer is negative. Therefore, the energy of the photon is insufficient to overcome the work function, and the electron will not be emitted. The answer is negative. Therefore, the energy of the photon is insufficient to overcome the work function. Right. Any questions on this?